So thank you, everyone, for inviting us. It's a great pleasure to be here. And the title of the talk, as you can see, is Quantum Machine Learning, What's Done and What's Left. But since this is a conference about natural language processing, I choose to focus a little bit more on quantum natural language processing. Just a second. Fantastic. So a few days before the conference, I was on Twitter, and I saw some recent results in classical natural language processing. And these results were mostly due to neural network. So as you can see here, this new Google neural network image gen can generate very realistic images from text. And this other neural network here from a picture can describe and understand the semantic of the content of this picture. So I said, well, probably the right title for this talk is Quantum Machine Learning, Algorithms for Quantum Natural Language Processing, What's Done and What's Left, because I won't talk much about neural network and quantum neural network. We can discuss that in the conclusions. But I will talk mostly about algorithms that are not neural networks. So the table of content for today is the following. I will start by introducing the toolkit for quantum machine learning algorithms. And then I will present some results organized in unsupervised and supervised methods. And there, for the what's left part, I picked some just two algorithms, LDA and CCA, which we will describe later. And then I will present some recent results in quantum algorithms for spectral sums. And then I will present a framework for running experiments on quantum algorithms without a quantum computer, and then obviously the conclusions. So let's talk about the computational model that we use in quantum algorithms. So we work in this Curran model. So let's say that this AIAN is a list of numbers written in binary expansion. We assume to have access to this kind of mapping here. So if you have a quantum state ket I with a query to this oracle, you are able to produce a quantum state ket I AI. And the important thing about this is that the preprocessing time that you need to spend is proportional to the length of the vector. And the space, obviously, for storing this data structure, which you can think of as a circuit, is also linear in the length of the vector. But the query time, so the depth of a quantum circuit, will be mostly proportional to log n. And also, like, you will use only log n qubits for this mapping in your quantum computer. A new result that dates to 2019, which is very nice, I think, is that there are certain architecture proposed by Giovannetti and others that have been recently studied in a realistic noise model. And Han and others, they were able to prove that the fidelity of this circuit scales very well. So it's proportional to the log of the size of the data structure. So if you give me this data structure, I can build another quantum circuit on top of it, which basically creates amplitude encoding of quantum state. So let's suppose that we are given a matrix X of n rows and d columns. So you can imagine that you have a data set of n vectors and d features. Well, I can create a quantum state xi where basically I'm putting in the amplitudes the features of a vector. So as before, the preprocessing time is proportional to the size of a matrix and the space as well, but the query time is proportional to the log of the size of a matrix. So most of you are familiar probably with HHL, this breakthrough in 2009 that allowed to produce quantum state proportional to the solution of a linear system of equations. In the next 10 years, people ameliorated these algorithms, and the state of the art now is called singular value transformation. So if you give me a matrix X and a quantum state V, then I can produce a quantum state Z that is epsilon close to the pseudo-inverse of A. So, or if a matrix is square and invertible, you can just put an inverse if you're more comfortable with that. And the runtime for this, this algorithm depends only linearly in the condition number of a matrix, so like the ratio of the biggest singular value over the smallest singular value, and depends linearly on mu, which it's, you can think of it as a matrix norm. Think of it as the Frobenius norm, so like the L2 norm of the matrix. And depends only logarithmically in the approximation error that we want on the final quantum state. More generally, if you give me a function that I can approximate with a polynomial of degree d, I can apply this function in a quantum computer to all the singular values of the matrix A, and then I can basically create a quantum state that is proportional to the function applied to the matrix applied to the quantum state. So another important tool that we use for writing new quantum algorithms are these subroutines here, which basically, given quantum access to a matrix and given to indices, we are able to compute either the inner product of rows of a matrix, either the L2 distance between vectors, between rows of a matrix. We can compute a quadratic form in this runtime here. And the most important thing that you have to look at is basically that these runtimes do not depend on the length of the vectors, but depends only on the approximation that we want in the distance or the inner product that we are computing. So for the quadratic forms, if we want to have matrix inverse here, we pay a cost of the condition number. And then there is another distance induced by a matrix A that has this runtime here. And where, again, you can think of mu as this Frobenius norm of a matrix. It depends on the preprocessing that you choose to do for your quantum algorithm. And these are basically swap test or Hadamard test, if you are familiar with these names, on steroids. So basically, we apply amplitude estimation on these things, and we make sure that that the failure probability is bounded correctly. And obviously, we can produce these things coherently in superposition. So as a way to output information from the quantum computer, we perform tomography. Tomography in general is quite costly, but if we just assume to perform tomography over pure states, then tomography becomes linear in the dimension of a Hilbert space if we want an L2 error on the vector that we want to know classically. And if we want to have an L infinity error, which means that we want to have epsilon error on every component of vector x, then the runtime for this procedure depends only logarithmically in the size of a Hilbert space and quadratically in epsilon. It's quite unlikely to decrease the dependence in epsilon of these subroutines because these are classical subroutines, so you cannot apply amplitude estimation on these things. And this epsilon square comes from a Chernoff bound. But we have some experiments showing that at the end of the day, this epsilon square won't be a big factor in the runtime. Other subroutines that we will use for later in the trace estimation spectral sums part are subroutines to estimate the trace of a matrix for which we have quantum access on. And there is also a subroutine that you can use to estimate the trace of A transpose A. And the nice thing of this subroutine here is that there is a quadratic speedup in the size of a matrix in order to get a relative error. So let's start from unsupervised methods because, as you know, anyone is full of correctly supervised data. So in this setting, we are given only a matrix X with no labels. So what we can do here? OK, so names that are highlighted in yellow are basically things that are left to do as a quantum algorithm. And when it's written, GAP is basically stands for Generalized Eigenvalue Problem. So if we remove this matrix B here, this is a normal eigenvalue problem. So this matrix W is the matrix of the eigenvector, and this matrix lambda is the matrix is a diagonal matrix of eigenvalues. But the generalized version of this problem has this other matrix here, which we assume to be invertible. So 2 years ago, we presented some results in this framework of tools that we presented now. So we have principal component analysis, correspondence analysis, and latent semantic analysis that you can also find in quantumalgorithms.org. And then we have spectral clustering, k-means, expectation maximization, kernel PCA, and factor analysis. So most of you will probably be confident with k-means. Spectral clustering is basically k-means applied in a high-dimensional feature space. And expectation maximization is a sort of generalization of k-means, which we will soon see in the next slide. And then we have independent component analysis, which I think is quite relevant for natural language processing. And independent component analysis is used for things like you have sound that comes from a room full of people that are talking, and you have a set of microphone in the room, and then you are able to disentangle the speakers and recognize each speaker singularly. And this LDA, latent Dirichlet allocation, will basically something that we will discuss soon. But first, I have to talk about expectation maximization. And then information bottleneck methods are a whole set of algorithms that stemmed from information theory. I fall in love a few years ago with this subject because I find it very beautiful. And inside this information bottleneck method things, there are many algorithms that are potentially relevant for natural language processing. And last but not least, I think that there are still many areas for which we don't have any quantum algorithm at all. For instance, there are no so far quantum algorithms for group theoretical machine learning, no algorithms for hierarchical clustering, and for graphical models, which is a very broad field in classical machine learning, there is only one paper that allows to fit the model of a Markov random field. And we have only one paper in topological data analysis, or actually a few papers. So let me show you graphically first what is expectation maximization, if we can run this thing. Yes, it works. Great. So basically what we are doing here is we are given this set of points, and we want to learn a description of these three clusters that are here. So what we do want by description, I mean we want to know the center of these clusters, but also a sort of description of what is the shape of the cluster. So in mathematics, this thing is a covariance matrix of this Gaussian distribution. So what we do, we start from a random guess. We pick a point as a guess for a random centroid for these covariance matrices. And then we pick the identity matrix as our initial random guess for the covariance matrices. Yeah, let's run it again. And then what we do is we compute somehow the distances between all the points and all our K clusters. We estimate the covariance matrices with a complex mathematical step, which I won't delve into. And then we update our model by moving the centroid and updating the description of the covariance matrices until we reach convergence. And when we reach convergence, basically we stop. Okay? So mathematically, what we are doing here is we are fitting with a maximum likelihood estimation a Gaussian mixture model. So the Gaussian mixture model, the model itself is composed by theta, which is basically tells you the proportion of density between different clusters. This mu I, mu k represent the centroid of the various Gaussian distributions, and these sigma 1, sigma k are the covariance matrices. So these are the things that we want to learn. And yeah, we have k labels, and this p here, this probability distribution is the probability that a point xi in our data set comes from the Gaussian distribution described by mu j and sigma j. So the classical algorithm for fitting this model has a runtime of d squared kn, where d is the number of features, k is the number of different clusters, and n is the number of data points in our data set. And the quantum algorithm that we were able to come up with has a runtime of d squared k to the power of 4.5, depends on this gamma factor, which is a parameter that depends on the data set, which we will discuss more in the experiments, and has only logarithmic dependence in the number of data points. So the algorithm is roughly this one. So instead of showing the algorithm for expectation maximization for fitting a Gaussian mixture model, I will just present a simpler algorithm, which we also published in EURIPS in 2019, which is k-means. It's the quantum version of k-means. So it's an iterative algorithm where we start, as I said before, from a random guess of just the centroid for our clusters. We compute all the distances between all the points and all the centroids. And then we assign each point to the closer centroid. And in step number 2, we update our description of the centroid by computing it, like the barycenter of the cluster. Questions? Is okay? Do you know? Yeah. Yes, this is k-mean, and for which we also have a quantum algorithm. And morally, quantum expectation maximization and expectation maximization for fitting a Gaussian mixture model is the same thing. You don't only compute the distances, you compute something that is called the probabilities, the responsibility. And you don't only update the centroid, but you update also the covariance matrix. But what I want to say is that these algorithms are very similar to each other, and in fact, they are part of this whole family called expectation maximization algorithm. So during the expectation step, you compute a lower bound for the likelihood function. And during the maximization step, you update the parameter of your model, and you maximize the likelihood. And you repeat this process until convergence. Why I wanted to show you expectation maximization? Because this algorithm, LDA, for which we don't have a quantum algorithm, could potentially be quantized using expectation maximization. So what is the model of LDA? Well, basically here we are given a corpus of text, and we want to learn the parameter that generated this corpus of text. So in this corpus of text, a single document is a mixture of topic, and a topic is a mixture of word. So we want to find the parameter alpha and beta that generated the corpus following this process here. So every document in the corpus is generated by first deciding the length of the document. So by first deciding how many words are in the document. And then we sample theta from the Dirichlet distribution given the parameter alpha. And the Dirichlet distribution is a very complicated thing, but you can think of it as a way of sampling multinomial distribution. So this theta here is a vector that sums up to 1. So it's basically a probability distribution. And this thing will be used to sample each word. How? Well, every word is sampled in the following way. First, we select a topic according to the multinomial that we just sampled. And then, given a topic, we pick a word according to another multinomial distribution. So this beta here is a matrix of size k times v, where k is the number of topics that we have, and v is the number of words that we have in our corpus. So what we want to do is we want to find the parameters alpha and beta that generated according to some maximum likelihood principle, a corpus that we are given. So graphically, you can think of this process in the following way. So again, this beta and alpha are the parameters that we want to learn. This big square here is our corpus, and this theta is the distribution over the topics. And yeah, this word here is given by a topic and the matrix B. So the matrix is basically a set of multinomial distribution, one for each topic. And fun fact, this LDA algorithm has been used to understand like topics in all the patents related to quantum dots. And these are the topics. It was just a fun thing. So let's switch to supervised learning now. So along with a data set, matrix X of n vector and d features, we are also given either the labels or a regressing variable that we want to learn. And here is the list of algorithms that we have and algorithms that we don't have. So 2 years ago, we presented here slow feature analysis, the quantum version of slow feature analysis. And in the same paper, we also presented a very simple classifier that can be used with slow feature analysis. Slow feature analysis is basically an algorithm for dimensionality reduction. And after it has been proposed, people discover that it's actually equivalent. So it fits the same model as Fisher linear discriminant. So we have now a quantum algorithm for Fisher linear discriminant and a quantum algorithm for slow feature analysis that are basically doing the same thing. There is only one quantum algorithm for support vector machine, apparently. But classically, the versions of SVM that we have are almost so many. So I think that there is space for new quantum algorithm in this domain. And then for the things that we don't have any quantum algorithm for CCA, so canonical correlation analysis, which is a very powerful algorithm. I think that has a generalized version, a kernel version, and we don't have algorithm for this, but I think only some ideas. Strangely enough, there's no quantum algorithm for nearest centroid, which is a very simple classical algorithm. There is one paper on quantum algorithms for fitting a decision tree, but I think that the way you can fit classically a decision tree are many. So I think also in this space, there is space for more quantum algorithms. And again, there is another generalized eigenvalue problem for fitting partial least squared. Speaking about the areas for which we don't have quantum algorithms, again, there are no quantum algorithms for group theoretical machine learning in the supervised setting. Sorry, this should not be here, because yeah, clustering is belongs to the unsupervised section. And again, no quantum algorithms for topological data analysis and graphical models. So this is the description of the canonical correlation analysis. So we are given basically two metrics, X and Y. They have the same number of rows, so the same number of samples, but they have two different feature space. And basically, we want to learn a hidden variable model that allows you to explain with one feature space the feature space of the second random variable. Mathematically, this thing is described by finding two vectors that allow you to maximize the cosine between the matrix X times the vector Wx and Y times the vector Wy. How do you do this? Well, classically, you solve a generalized eigenvalue problem. And basically, this is an instantiation of this generalized eigenvalue problem where the matrix sigma x y, sigma yy, and sigma yx are covariance matrices and cross-covariance matrices, basically. And after many years, the runtime for the best classical algorithms, which I think touch some lower bounds, depends on the sparsity of the two matrices, depends on the square of the square root of the condition number of either one of these two matrices here, and this rho is something like a spectral gap of a product of X and Y. So, sorry, yeah. I think that there is a way to quantize this algorithm because it's very similar to algorithms that we already quantized. And it's very powerful because it has many applications in natural language processing. These are only a few papers that I selected. So it's mostly used for settings where you need explainability about the decisions that you need to make. And sentiment analysis, cross-domain sentiment classification with word embeddings are only a few applications that you have. So let me switch to, question. 5 minutes, okay, thank you. So another section of this talk where I present some results on spectral sums. What is a spectral sum? Well, it's basically a sum of a function applied to the eigenvalues of a matrix. And if the matrix is not symmetric, basically what you do is you sum the singular values of the matrix. Very simple. So one example of this spectral sum is basically this log determinant. So, well, the log determinant of a matrix is basically the sum of the log of the eigenvalues. And the best classical algorithm has a runtime that depends on the sparsity of the matrix, square root of the condition number, and depends on epsilon square, which is the approximation error that you want for the log determinant. And the quantum algorithm that we came up with basically offers you quadratic speedup in the approximation error. Why I selected this quantum algorithm here? Well, because the log determinant is an important tool in many other machine learning algorithms. So the hope is that it could be used for as a subroutine in other quantum machine learning tasks. And I find it very didactic because in order to come up with this runtime here, we actually had to quantize 4 different classical algorithms that you can find in the appendix of our paper with Changpeng. And the best quantization turned out to be the following. So you create a quantum access, like a block encoding of the matrix A, which you can think of as way to embed your matrix in unitary. And then you apply the singular value transformation of a polynomial that approximates the logarithm to your block encoding. And then you use the subroutines that I presented before to estimate the trace of a matrix. And this turns out to be the best quantum algorithm for the log determinant. Well, in the same paper, you find slightly different algorithms for computing the Schatten p-norm of a matrix, which is basically a function, in this case, is monomial, so like x to the power of p. The von Neumann entropy, there are so many papers, quantum algorithms for estimating von Neumann entropies in many different models, the trace of the inverse, and counting triangles. And now we are working on applications of these quantum algorithms, but also new quantum algorithms for estimating, for instance, the log determinant of non-square matrices. And this actually turns out to be far from trivial. So let's talk for 3 minutes about experiments. So we do not know how to compare the runtime of a quantum and a classical algorithm. So our proposal is to estimate the query complexity of a quantum algorithm by simulating the error that you have in your quantum computer. And how you do that? Well, you simulate the same error that you have in all this procedure that I presented before, and you see whether you can reach the same accuracy in a specific machine learning task, also with a simulation of your quantum algorithms. In this way, you are basically able to estimate better the parameter that governs the runtime of the quantum algorithm. And how you do that? Well, the query complexity is given by a theorem. The experiments are, can be done with a framework that we are presenting now called sklearn, which is actually public since today. And you can find it on this address here. And then with the knowledge of the circuit, you are basically able to estimate the gate complexity of a quantum algorithm. So I don't have time to present the results of this experiment here, I think, but it's basically a simulation of a quantum algorithm used to for the task of speaker identification problem. Long story short, with a quantum algorithm, we are almost able to reach the accuracy of the classical algorithm. And thanks to this simulation, we are also able to estimate the parameter of the runtime for the quantum algorithms that I presented before. I don't have time for this slide. These are a few references that for the algorithms that I discussed about. I contributed to the first 5 papers that you can find here. And you can find at this address here many more quantum algorithms. Most of them are for machine learning or can be used for machine learning. So conclusions. Well, quantum machine learning algorithms are potentially useful for explainable natural language processing. So I said that I won't be talking about neural network and quantum algorithm for neural network in this talk, but what I can say about this topic is that the quantum way, or the quantum way that we propose for quantizing a neural network is basically quantizing the inner product estimation that you have at all the steps of the training of a neural network. 1 minute. Thank you. So, long story short, don't use neural network if you want explainability. You already know this. So conclusion, there's a lot of work left to be done in natural language processing, LDA, Word2Vec, circuit for loading data, CCA. And I think that now the problem is also to study how to implement this algorithm on real machines. And don't be scared by the fact that in this algorithm, in this model, we assume fault tolerance, because there might be probably a way out of it. So hypothetically, we hope for a way to go from a noisy quantum computer to a fault-tolerant quantum computer, but some of these algorithms could still run with an advantage on a quantum computer. So thanks for your time.